Welcome to module 44 of Database Management Systems course in the IIT Madras online BSc program. We have been discussing about indexing and hashing, and we did the first three modules we have done in this week on B plus 3, culminating in B plus 3 index files for persistent data store, and we looked at B tree also in the last module, but our primary objective was to create index files and data files with efficient structure, which is the B plus tree as we have learned. We will introduce another concept here which can help in indexing operations known as hashing. You may be familiar with a little bit of hashing, hash table, hash maps and so on. So, we will talk about static and dynamic hashing and compare between ordered indexing that we have discussed so far and hashing, and introduce the concept of bitmap indices as well. So, static hashing, the hashing per se. So, what is hashing? In hashing, we have a domain of values which is normally very large, right. So, if that domain were small, then we could take each and every value and used it as a array index to do a random access. It is again, how do you make search efficient? That is a basic question. We could keep the data in an array, so that the value of that index coming from the set of possible values in D could be used as the address, right. But usually that is not the case. Oftentimes this domain of possible values is too large, and you have very small actual data that you use, right. So, think about names. They could be of practically any length. Even if you put some limits, it can go up to 30 to 40 characters very easily for many people, right. So, you can think of, if I say it, even if it is 20 characters and you have 26 letters in the alphabet and the blank, so 27. So, it is the first place can be taken in 27 ways, second in another 27 ways and so on. So, it is 27 to the power 20 is the kind of size of the space that you are talking of, but you will possibly have only a few thousand of them. So, you take, instead of using D as an index, values of D as an index, you use a function that maps the D onto a range of small range of values. So, you have different names here, you map them to a range of say 16 values called hash values, hash keys. So, that this function does something with the value in from the D and produces a value in between 0 to n. So, this is an example being shown. So, John has gets a value 2. So, that is where you are expected to get the details about John. Lisa has a value 1, this is where you get the details. Sam has a value 4. So, this is where you get the details. Sandra incidentally under this function has a value 2. So, two distinct keys, John Smith and Sandra D, both actually generate the same hash value. So, if I have two keys which are unequal and if they have the same hash value, we say a collision has happened, a collision has taken place. If a collision has taken place, then we have not been able to resolve and find, we will still have to go something else to do that, but this will have to be a limitation, or this will have to be a basic property of the hash function, because you are taking a large domain of values in D and mapping it to a small domain of n plus 1 values. So, there will be some, for some keys it will always have a collision, and how do we manage that efficiently is the will give the efficacy of the hashing. So, the values, the index that a hash actually takes you to, maps you to, is a bucket. It is considered a bucket where one or more records can be stored. Right. Typically, we take the bucket to be a disk block, again the question of transferring between the memory and so on. So, a hash file organization will have this hashing function. So, you have the key, you do the hashing, you get the bucket, and there you find the record, right. Now, naturally, as we have seen, records with different key values may be mapped to the same bucket. So, the bucket has to be searched sequentially to locate a record, right. So, in one part you gain by quickly coming to a subset of values. In the other part, you will have to pay if your bucket is very full or if you have too many buckets at a given hash value. So, example. So, our instructor table using the department name as a key, right. So, as a department name is a key. So, let us say there are 10 buckets. So, what we do is the department name, say if I say music, then each one of them has a ASCII value, binary representation. We take that as an integer, right, and then we add them together, sum them together, the ASCII of m plus ASCII of u plus ASCII of s, like that. It becomes a large number, and then we do a modulo, that is we divide by 10 and take the remainder, because there are 10 buckets. So, if there are 10 buckets, the indices are 0 to 9. So, if I do a modulo, I will get a value between 0 to 9 and I use that as a value. You can check out, but these are the computations of different names of departments that we have hashed through this process, that you take the ASCII value of every character in the name as an integer, add them, divide by 10 and take the residue, take the remainder, right. So, we will keep the records according to this. So, there are different buckets, 8 are shown here right now. So, music has a hash value of 1, so it goes here. History has hash value of 2, it goes here. Computer science has hash value of 6, it goes here. Interestingly, physics and electrical engineering both have hash value 3. So, both of them go here. So, once you come here, you will again have to search linearly, you do not know. So, this is the collision that is happening. This is what puts 2 or more distinct values in the same bucket. But this is how it can be organized, and you can see that while searching linearly within a bucket is certainly over it, but it is also true that if I have an appropriate hash function, then out of n bucket possibilities, n minus 1 have got eliminated. So, there is a large number of keys which have got eliminated. So, the linear search, even though it is required, will be done on a very small set, relatively small set. Now, naturally, there are other than collision, there are certain, naturally we would want hash functions which do not give a lot of collision. So, what will be, there will be some other desirable properties. For example, in the presence of collision, which is unavoidable, the number of keys that map to a bucket should be more or less uniform. If it is not, then one bucket will start growing larger and larger, and it will overflow the block size. So, I have to have another block as an extension of that bucket, and so on and so forth. So, this uniformity of hash values is a very desirable property of a hash function. Right. Similarly, a hash function is called ideal if every bucket will have the same number of keys, and typically only random functions are behave in that way, and of course, we cannot just work with random functions as such. Now, if a bucket has too many entries, it could happen in multiple ways. One could be is because you have insufficient number of buckets, that is, you are trying to map to a very small range. So, you will have much higher amount of collision and buckets will become full very easily. It could happen because the distribution is skewed, it is not uniform or not nowhere near uniform. There are multiple records which have the same key value. For example, let us say we were looking at the department name, and let us say the mechanical engineering department have 150 instructors, whereas music department has 5 instructors. Naturally, the data inherently is skewed, right. So, either you have you know the statistics of this data distribution and use that in the hash function, or you will get naturally very skewed result in terms of number of records going to the same bucket. It could also happen because of the choice of the hash function, because some hash functions give a better uniform distribution, some give less, but it is a situation we will have to live with all the time. So, the choice is to have overflow buckets, that when it falls here you are full, very naturally you will have a pointer to go to the next. Of course, this is increasing your cost dramatically now, because you are searching through a bucket in a linear form, okay? And as you do that, so you have more and more in the chain, you have those many additional block transfers to be done to memory, because if every bucket is the size of a block, one you have brought, you did not find it there, you have to go to the next, again keep on doing this. So, overflow handling is a problem in this scheme, which is otherwise called a closed hashing scheme. There are alternates to that, but they are not suitable for database application. So, this hash indices, this hash values, I am just to note that can be used not only for file organization, but you can use it for basic index structure organization also, right, because that is quite understandable, because in either case you are basically doing a search operation, and hashing is a shortcut, efficient shortcut for searching a key from an appropriate bucket with the power of this mathematical hash function. Right. So, this is an example here of the earlier one. Here we have organized the records according to the ID of the employee going to different buckets, and the computation is you add the digits. So, for 76766 you add the digit 7 plus 6 13 plus 7 20 plus 6 26 plus 6 32, right. So, 30 you get 32, and then you do 32 here, you can see mod 8. So, which will give you 0. So, bucket 0 has this. So, that is how you do. Now, you would normally expect this to be pretty uniform across values, but the fact is this kind of IDs are not generated in that way. It may have some other bias to do that. So, given this data, you can see that bucket 5 has 4 entries, right, whereas the bucket size is 2. So, it has to take care of a overflow bucket to go through. So, additional block access, and if you increase this more, it might increase even more. So, in summary, the static hashing which maps search key values to a fixed set of bucket addresses becomes a problem, because once a bucket starts getting more and more records concentrate on that, you have to make that overflow chain, which is so. And also the fact that the database is a dynamic entity. So, initially a database is small, so you need a small number of bucket. As it grows, the performance will degrade. If you allocate initially itself that I will allocate these many buckets with the anticipated growth, then there is a significant amount of space that is wasted initially, and in fact, in many cases you do not know what that growth could be. So, the basic problem lies with having to deal with a fixed set of buckets in case of the static hashing. Okay. So, what would be preferable if we could change the number of buckets dynamically? Now, the number of buckets, just to recall, is the range of the hash function. Right. So, if I change this n, naturally I will have to change the hashing function and rehash everything. For example, in the last ID case we were doing, adding the digits and doing a modulo 8. To increase, we at one point we decide to do modulo say 12, that will increase 4 buckets 50%. But as we do that, the hash values will change. So, all reorganization will be required. So, the static hashing has a problem with the growth. It is good fast for, I mean, kind of, if your database data is more or less static, which is normally would not be the case for most databases, but in general it will have a problem with this growth. So, we move on to dynamic hashing, or also called extendable hashing. In extendable hashing, hash function is not thought to be changed, you cannot do that. It generates a value over a large range. That is, as if you are thinking that there is a virtual space of buckets. Right. So, you can say there is a b bit integer, the range is a b bit integer. So, what we are saying is hash function goes from d to 2 to the power b. If it is a b bit integer, then there are 2 to the power b possibilities, and say with the value 32. So, it is now it's quite unlikely that most databases will require so many buckets, they will not, but this is what is you start with. So, that is your function, that is how you design the function. The trick lies in the next step. You have 32 bits, but you do not use all of them. You just use a few prefix bits of the index, rest of them you ignore. So, maybe if you want to have 4 buckets, then you use 2 bits from the front and ignore the remaining 30. What does that mean? That means that every 2 to the power 30 buckets are getting collapsed into one bucket. They are getting collapsed into one bucket, right. So, just if you would be comfortable with an example, let us say my b is 3, my b is 3. If I use just a single bit prefix, then I have a bucket 0 and a bucket 1, 2 buckets, right. So, 0, 1, 2, 3, all these 4 buckets, virtual buckets, map to bucket 0. 4, 5, 6, 7, all these virtual buckets map to bucket 1. Instead, if I use 2 bits instead of using 1, then what happens? I have bucket 0 here with 0 and 1, I have bucket 1 here with 1 and 2, I have bucket 2 here with 4 and 5, I have bucket 3 here with 6 and 7, right. So, you can see by what I am trying to show you is by the choice of how many bits in the prefix you take, you do not need to recompute the hash function but by changing this number of bits you take from the prefix can actually change the buckets that you use. Right. Now, so it could be anywhere between 0 to 1 bit to 32 bits, and as I grows, the number of prefix bits that you are using, as that grows, then you will shrink the database size. I am sorry, at that grows, you have more number of buckets available, and if that shrinks, there are less number of buckets available. So, the database size, based on the growth and shrinkage of the database size, you could control this value of I. Now, naturally, even in this, it is possible that so you have now you have these set of prefixes that you have chosen, and then you take the buckets, map to them. Now, it is possible that all the prefixes that you have taken may not have separate bucket, for the simple reason that when you make your choice of the prefix bits, you can use 1, you can use 2, you can use 3 like that, but for that the number of buckets you need is 2, 4, 8 like that. As you increase 1 bit in the prefix, your number of bucket requirement doubles, right. But you may not actually have that much of data to double or that much of space to allocate for buckets. So, you may be using 3 bits requiring 8 buckets, but you may actually be using 5 buckets. So, the actual number of buckets may be less than 2 to the power I. So, what does that mean? That some of these values from these I bits will have to map to the same bucket, right. That is a point we are talking of here. For example, here is an example with you have 2 bits used. So, the bucket address table, this is called the bucket address table, where you keep the hash value and the corresponding bucket pointer. So, in this bucket address table you have 4 pointers, but you have only 3 buckets. So, these 2, and we will see how that happens. These 2 are mapped to the same bucket, whereas 2 and 3 are mapped to 2 different buckets. Right. So, let us see, instead of going through the extended theory, let us quickly get to a point where we can. Now, searching is quite obvious, right. You get to this, get to the index, compute the hash, take the prefix as many bits as we are using now, go to that bucket address table, go to the bucket, and you have everything. Now, when you are trying to insert a record, that means you might need more bucket. There are 2 possibilities. One is the number of prefix you are using is greater than what you actually have in terms of the buckets. So, it is possible that you can allocate a new bucket. As you allocate a new bucket, you have to reorganize the records between the earlier bucket and the newly allocated bucket and recompute the new bucket, simple. If it is same, that every index points to one bucket only, then you do not have buckets left. So, you may not be able to do a split for this insertion. You can create an overflow bucket, but the other option is you can increment the value of I, you can use one more bit. So, the bucket address table will become double and you will reorganize the buckets in the bucket address table, so that your bucket address table is becoming double, but your value of actual buckets is increasing only by 1, because that is what you need. So, you do not unnecessarily create empty buckets and push in there, you do not need to. Rest of the, that is I plus 1 minus I j plus 1 or I minus I j number of buckets will pointers will point to the same sum of the same buckets as they exist. Deletion happens by the same logic, rather I am keen to go to an example. Okay. So, let us start with this in the next couple of minutes. So, this is a 32-bit hash key generated for the department name. Okay. So, we will use this as our data. So, this is the initial, you have 0, this is the initial bucket, this is the data to insert. So, we will insert Mozart, Srinivasan and U in this order. So, Mozart is music, Srinivasan is computer science and U is in finance. Finance, music, computer science, 1 bit, 1 bit, 1 bit. So, you can see that finance and computer science will clash, will be in the same bucket, and music will be in a different bucket. Right. So, that is what has happened. They are, and this is in music is in a different bucket, because it has a value 0, and computer science and finance has a value 1. This 1 marks how many bits are being used to come to this bucket. So, in both of these, this is 1. Now, we want to insert Einstein onto this. So, what is Einstein? Who is I mean, where is Einstein? Is in physics, right? Physics, this is 1. Right? So, when it comes to that, if we go back a slide, we will see that physics is 1, computer science is 1, finance is also 1, right. So, Einstein needs to go in here, where we have assumed that every bucket has 2, size of 2 only. So, this bucket is already full. So, Einstein cannot go in here. So, what I do is I increase the value of I, that is the number of prefix bits we are using, and so therefore, your bucket address table now has 4 entries. You had 2 buckets, and because of this need to insert a new record, you need another bucket. So, you have created another bucket. Now, let us look at the values. Physics is 1 0, that is 2, music is 0 0, that is 0, finance is 1 0, that is 2, computer science is 1 1, that is 3. Right. So, this computer science comes here, this is 3 2 1 0, physics and finance come here, music remains in 0, no change, and so this we had to create because of inserting this record. So, this goes separately with index 2, this also is having 2, but we do not need to create a separate bucket for 1, the value 1, that is, which will mean a prefix of 0 1, that is till we get electrical engineering actually, and we let both of these map to the same bucket. So, if you look in carefully, here we are saying 1, that is one bit is used because the second bit is ignored, because you have multiple are mapping here. So, 0 and 1, out of 0 and 1 you are just using the 0, from 0 0 and 0 1 you are representing by 0. So, it is 1 bit, whereas these two are 2 bits. Right? It is as simple as that. So, you can insert gold and LZ records. Gold is in physics, clearly goes in here. LZ is in history, history is 3. So, that can go in here, and you can see that again we increase the number of bits. Again, this is using one prefix only. So, 4 values are here. This is using all the 3. So, 1, this is using all the 3, this is using just 2. So, you have 2 values coming here. So, it keeps on going in this manner. You can step by step work out. We are including all of these. Now, when you included all of these, you again had a overflow with brand, because computer science needs another block. Now, you may use 4 bits, but you chose not to immediately increase to 4 bits, because you can see that well, there is already number of unused stuff here, but it is just that the keys are biased towards this side. So, instead of increasing the bucket address table size, reorganizing it, you use a overflow bucket. So, it is kind of a trade off between the two as to which one you want to do at different stages. Finally, you insert KM and go through the steps carefully, so that you will know that well, what all. So, the comparison is pretty straightforward. Obviously, the dynamic scheme works better, though change of the bucket address table is an expensive operation and has to be done with judgment, and comparison of ordered indexing and hashing clearly shows that hashing would that way be quite good, because it does not require the cost of periodic reorganization. Relative frequency of insertions and deletions can be considered for that, and depends on also the kind of queries you have. Like hashing is good to retrieve records with a specific value, because you need to hash. Range queries will be good with ordered indexing, because you need to go over a certain range. In spite of the power of the hashing, in practice though it is not so widely used in the big databases. Like I have just given some information of what, and so these schemes exist, but this is really what most of your major database provider actually do. One small closing concept, this is called a bitmap index. The idea of a bitmap index is certain attributes have a fixed and small set of values, like gender, only 2 possible values or maybe few more. The countries 170, 200 values, states of a country maybe 100 values, certain income levels, maybe 20 income levels and so on. So, why, since when you have this small set of enumerated data like this for an attribute, then the idea is, why do you keep on writing that male, 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 female, 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 female like that? Why do you replicate? Instead, you could keep this in a different way. You can just turn the table. Instead of mentioning the value of an attribute for a record, instead you look at from the attributes perspective, you look at whether a given attribute value is present for that record. So, simple example. So, number the records in some arbitrary sequential order, and then you try to see, this is going from left to right. I am looking at, so I have a bitmap which is the number of records that I have, and if m male is present, I put a 1. This is female, I put a 0, this is female, I put a 0, this is male, I put a 1, 0. Similarly, in female, I will just have the other places as 1. So, when you have to search for a particular, I mean, is male, all that you need to do is to collect the bits which are indicative, whose positions are indicative of the record number. Similar thing you can do for income level. What is actually far more interesting is you can actually do, and if you want to say the male and income level 14A, then there are 2 bitmaps of the same size, the number of records in the collection, you can just AND them. So, logically AND them, and wherever you get a 1 is the other position, other indices of the records which have that. So, these are more details in discussion, and there are several algorithms to efficiently compute this through lookup tables and so on. So, bitmap is a nice idea to expedite the access of a number of possible attributes which have fixed small set of possible values. So, with that we come to the end of this module. Thank you very much for your attention, and we meet in the next module.